Good morning, everyone. I'm going to do a quick check if online can people hear us okay.
Okay, we have a confirmation from Jan.
Perfect.
So far, so good.
So far, so good. Okay. Well, thanks everyone for attending today's. There's a two-part session on the Polar Night Experiment Aircraft campaign. We'll do 6 talks before lunch, then we'll break for lunch, and then we'll finish in the afternoon with a few more talks, as well as a follow-up discussion session. So the idea behind the discussion session is it's open to everyone. It's an opportunity to talk about some more of the details, planning, or different opportunities that might arise from this campaign. So we're really excited to talk about this, the PONEX campaign, which is planned for January 2026. And I suppose I should introduce myself. I'm Zen Mariani. I'm a research scientist at Environment Climate Change Canada. And my fellow conveners are Professor Kaley Walker, University of Toronto, and Natalia at NRC. And so with that, I'll get started on this first talk. Is just a very general overview. So what is PONEX and what are we planning to do in January? So the PONEX team has been growing since 2021. So really, there's a long list of contributors of people, different scientists from both Environment Climate Change Canada, NRC, several universities across Canada, as well as institutions in the US and universities in the US that are participating in PONEX. So this really is a huge collaborative effort of getting all the different instruments and scientists involved for PONEX. And PONEX is a direct result of the NASA Atmosphere Observing System. So on Monday, Adam gave a great presentation that went over exactly what is AOS and what is HAWC. So I'll just very quickly go over what AOS is again. Is that essentially that was a comprehensive mission designed to address 2 of the 5 most pressing satellite Earth observation needs, which are highlighted on the right there. So primarily to address aerosols and clouds, convection, and precipitation. So this aligns very well with ECCC's current science strategy and priorities, which is why obviously there's a lot of interest at ECCC. And this leads us to HAWC, or the HAWC. So it's the high altitude aerosols, water vapor, and clouds. And again, this Adam gave a great presentation on HAWC. And so there is funding from the Canadian Space Agency to support the HAWC mission, including the satellite instrument development, the science and application development, and also the sub-orbital component. So that's where PONEX fits in. The sub-orbital component essentially is the development and preparation and calibration of the satellite instruments. It consists of things such as, but not limited to, aircraft and ground-based campaigns for not just post-launch, not just after the satellite's been launched, but also pre-launch activities. And this is, it's a very collaborative effort. So we're engaged with NRC, NASA, CSA, JAXA, ESA, and the University Consortium. And over the past few years, one of the things that has been identified is that the Arctic region in particular is a significant CalVal gap when it comes to the AOS mission. And so that's where the need for PONEX has really accelerated. So if we talk about AOS and the HAWC, this figure on the left is slightly outdated. So I think Adam has a more up-to-date figure that does a better job showing some of the different instruments and satellite orbits. I'm going to focus on HAWC primarily. So what's shown on the right are the 3 primary instruments that Canada is currently contributing to the mission. There's TICFIRE, which is essentially going to measure far infrared radiation. There's ALI, which is the aerosol limb imager, and SHOW. And for the purposes of PONEX, if we want to perform calibration validation of some of these 3 instruments before they're launched, PONEX is going to focus on these 2, TICFIRE and ALI. So we're going to fly ALI on the NRC aircraft. And we're also going to fly an instrument very similar to TIC-FIRE. It's called the FIR-2, the Far Infrared Radiometer. Essentially, the FIR-2 is the ground-based precursor to TIC-FIRE. So before we build TIC-FIRE, we've already operated the FIR instrument in several locations across Canada. This is a general overview of how we got to PONEX, and it all started back actually in 2015. This concept of a polar night aircraft campaign was initially proposed by Alexei Korolev, who's going to be following my presentation. And then in 2018, ECCC, we acquired the FIR-2 instrument, so we began operating and testing it on the ground in the Arctic. In 2019, the CSA initiated plans for aircraft and ground-based campaigns for HAWC. In 2021, it was identified or demonstrated that a pre-launch campaign really was needed. So we need to test and calibrate these instruments before they're flown. There's been several suborbital working group meetings. And finally, in 2022, as a result of these meetings, the Polar Night campaign site was selected for an Inuvik in Northwest Territories. And then there's been some workshops. And then in 2024, that's when things have really accelerated. So the CSA HAWC Treasury Board submission was approved. And just this year, or earlier this year, there was the ESA Wafers aircraft campaign led by the NRC. And during Wafers, we have flown the FIR-2 instrument fully integrated on the Convair. So we've got our first airborne instruments thanks to the NRC team and UCAM. And so there's a talk that will be following Raphael, will be given in later today. And then currently what we're working on is the testing, calibration, integration of the remaining instruments on board Convair in preparation for PONEX. So the PONEX campaign, it will be using the NRC Convair 580 in Inuvik. The dates are January 8th to the 28th in 2026. So we will be up there in the dead of winter in polar night, just as the sun's about to come up. We have about 10 flights over 21 days. So we know, for instance, the first flight will be our familiarization test flight. And then flights 2 to 10 will be divided among the HAWC, EarthCARE, and science objectives below. So the team consists of about 36 people on site. That number is slowly growing. About 35 people that are actively engaged off-site, so not in Inuvik, but still engaged on a daily operations basis. And of course, a whole team of collaborators that will be looking at the data afterwards. The objectives of PONEX include the suborbital component. So it targets 2 satellite missions. First is the HAWC, AOS HAWC, with a focus on ALI and FIR. And the second is calibration and validation of EarthCARE observations. And that's something that my colleague Jiping will be talking about later this afternoon. And at the same time, there is a science component. So this is, Alexei Korolev is going to talk about this in more detail in the talk after this. But there's a focus on optically thin ice clouds, cloud microphysics, boundary layer dynamics, aerosol chemistry, transport of air pollutants, as well as a number of other science objectives that aren't listed on this slide. So this gives a quick overview. There's the NRC Convair aircraft, and that's the location of Inuvik. That's about the range. You can see those red range rings of how far the Convair can fly, and we're looking at targeting most of the flights over the Beaufort Sea, so flying to the north over the ocean. So the suborbital component is included in the HAWC budget, and this is through collaboration with NASA, JAXA, ESA, and the University Consortium. So for PONEX, the budget is just over $3 million. That's contributed from the CSA, as well as the European Space Agency that's contributing to do CalVal of the EarthCARE satellite. This, just want to note, this doesn't reflect the in-kind contributions from ECCC and NRC, which you see listed there. And there is separate additional funding for the universities to participate in the PONEX campaign, which is crucial for analyzing the ground-based instruments and some of the aircraft data as well. And this will also at the same time provide training of HQP, algorithm development, data analysis, and analysis of our ground-based site during the entire campaign. There's a modeling component as well. So we will be taking measurements of very unique atmospheric conditions. Essentially, this is going to be the first aircraft campaign during polar night that has ever been conducted. So every flight, we will be learning something new. It's uncharted territory in many regards. So we're looking at things like widespread OTICs, optically thin ice clouds, unique radiative signatures or radiative closure experiments as well, high impact weather. And in terms of the numerical weather prediction component, there's a lot of interest at ECCC in looking at the GEM cloud microphysics and parameterizations of the GEM model, as well as we will be deploying our experimental 1 kilometer high resolution model forecast runs over this domain that you see in the bottom left figure. So later this afternoon, please see Melissa's talk on the modeling component. And on the right-hand side, there is a link between the EarthCARE algorithm development and the ECCC model. So please see Jipeng's talk this afternoon. So this is my second last slide. Just wanted to mention there are opportunities for collaboration, especially here at CMOS. So we're very interested in external partners, collaborators, and data users are welcome. All the observations will be made available after the PONEX campaign. And so please contact us or come to the discussion session after lunch where we can talk about some of these details. For instance, campaign flight suggestions, comments, and so forth. And so planning for the campaign is ongoing. So now is a great time to get these ideas in and suggestions in before things get basically finalized. And if we look at the future timeline real quick, so this summer we'll be doing a lot of work integrating instruments on the NRC Convair. There'll be a campaign team and flight plans finalized by the fall. In October, November timeframe, there will be a PONEX workshop, and remote option is possible to attend. In November and December, there will be the test flights conducted in Ottawa by NRC, and then in January, the campaign starts. So I'll leave it at that. And just lastly, to highlight, PONEX targets the 2 satellite missions as well as the science objectives for CalVal, and this will be the first campaign to support the satellite CalVal and advance Arctic science based out of Inuvik. So thanks everyone very much. And if there's any questions, let me know. Yes. Oh, sorry, we're just going to get the microphone for people online.
Good morning. Thank you. My name is Catherine Boggs. I'm from Mount Royal University in Calgary, and I happen to be a geologist. I do a lot of work in the north, and I was wondering if there's a lot effort to do outreach with the people in Inuvik.
Yep.
Yes.
Definitely. Yeah, great question. Yes, we can talk about that more at the discussion session, but yeah, between the local organizations, the research licenses, as well as some of the other the surface sites that are in Inuvik or north of Inuvik, Trail Valley Creek, for instance. Yeah, definitely.
And then a follow-up is there any work towards developing sort of outreach citizen science projects for the school kids in Inuvik to be able to use the data that's coming from their area?
Do you want me to answer?
Yeah, yeah, I'll let you go ahead.
Basically, my group has done a lot of different interesting types of things, mostly in the Eastern Arctic. So it is on the list, but until we actually had a funding opportunity to be able to fund academic participation in this, there were a bunch of us who were participating in planning this event, having no idea whether we'd actually be able to go. So part of the outreach is trying to figure out by going and talking with the local representatives at the school or the school board to say, this is what we can offer. What would your classes be interested in, and how does it fit in your curriculum? That's the plan we were going to do.
Okay, I'd love to chat with you a bit more after that. Yeah.
Thanks. And if there's no other questions, we can move to the next talk, which will be given by Alexei Korolev. So we'll be switching to this is a remote talk. So let's see if we can get this to work.
Can you ask Alexei to share his screen?
Lexi, can you share your screen?
Just I'm trying to share, but this button is blank, so it doesn't allow me to get in.
So Alexi, we can click as you just let me know when you want me to advance the slides, and we can see it here.
You know, just I suggest to go. Just I uploaded my presentation, so just if you, I will control remotely slide sequence. Hey, great. So this presentation elaborates on previous Zen's introduction of PONEX, and I'm going to elaborate more just deeply about this PONEX field campaign, instrumentation, and flight operations to meet the project's objectives. Next slide. We'll begin with a brief overview of PONEX objectives. The overarching goal of the PONEX project is to acquire new knowledge needed to improve weather and climate forecast in polar regions through a better understanding of key physical processes and an improved presentation of those processes within numerical weather predictions and climate models. This newly obtained knowledge is particularly important for understanding of the phenomenon of Arctic amplification. The project objectives consist of two parts, as Zen mentioned in his talk. The first one is a sub-orbital objective focused on the performance and algorithms of HAWC instruments, ALI and FEAR, and CAL-VAL of the EarthCARE satellite. The second set of objectives is related to science of Arctic polar night environment, which can be broken into a set of sub-objectives related to obtaining new knowledge on the formation of optically thin ice clouds, mixed phase clouds, and their radiative properties, obtaining novel observations on Arctic surface emissivity and thermal profiles, study of the polar night aerosol properties, the chemical composition, concentration, and nucleation activity, ice nucleation activity, study polar night atmospheric chemistry and thermodynamics of polar night troposphere. To address this set of objectives, NRC Conveyor 580 was equipped with the following instrumentation. Next slide. This cloud microphysical instrumentation integrated on the Conveyor is shown in this table. It consists of three groups, just colored in highlighted by different colors. First group, first two is scattering probes for measurements of cloud liquid droplets in the size range from 2 to 50 micrometers. Second, 6 instruments are particle imaging probes for measurements of cloud particles from 10 micrometers to approximately 2 centimeters. And last 3 instruments are bulk microphysical probes for measurements of bulk liquid water content and total water content of clouds, bulk extinction coefficient, and presence of supercooled cloud liquid water. This set of instruments cover the measurements of the entire range of hydrometeors that could form in the Arctic atmosphere, and they cover from range from a few micrometers to a few centimeters. Next slide. The Aerosol instrumentation presented in this table presented in this. The first 4 instruments were flown on the Conveyor on this greenish table, And however, the last two are new installations. It's ATOFMS, is an aircraft aerosol time of flight mass spectrometer for measurements of chemical composition of aerosol particles in real time. And track, the last one, which is a time-resolved aerosol collector, which collects aerosol particles on a sequence of substrates up to a few hundred per flight. The collected particles will be explored later on in the lab under computer-controlled scanning electron microscope and in a diffusional chamber for the ice nucleating activities. Trace gas measurements, it's a table on the right bottom. These measurements will be performed with a set of instruments, and of all these trace gases, the water vapor is critically crucial for the PONEX objectives. And it will be measured by three instruments, Leica, Picara, and the Diode Laser Hygrometer, DLH. And the DLH is an open path hygrometer that's a new installation on the conveyor, and it allows measurements of water vapor down to a few tens ppm, which is this instrument is just has amazing accuracy, and that's what we need for Arctic environment, because water vapor measurements remains one of the very difficult tasks just in airborne measurements. Next slide. The set of PONEX remote sensing instruments is shown on this in this table on this slide. The PONEX mission critical instruments are Aerosol Limb Imager, ALI, and Far Infrared Radiometer, FIR. These are two, and the first two. These are two new instruments on the conveyor. Beside that, there are three radars: X-band, W-band, and K-band. And these three radars and the cloud LiDAR will allow a comprehensive remote characterization of cloud microstructure. HISRAMS, it's the last instrument in this table, is a multi-frequency microwave radiometer that allows retrieval of water vapor and temperature vertical profiles. Next slide. The flight operations will be planned based on weather forecast and satellite data. The flight plans may also be changed after takeoff based on in-flight updates. And there are two distinct flight regimes. The first one is weather flights related to cloud sampling, which involves a lot of aircraft maneuvering with ascending and descending through clouds. And the second one is clear sky regime, which will include extended horizontal legs at different altitudes. And the calibration validation of the EarthCARE may be associated with either of these two flight regimes. Next slide. So this slide shows the area of operation of the conveyor during PONEX. The red circle depicts the distance from Inuvik. The duration of research flight, the conveyor research flights will be during PONEX will be limited to 4 hours during remote during a distance to the alternative airports in case of bad weather. And during this time, during the 4 hours, the conveyor may go up to 1,000 kilometers away from Inuvik during for a return flight. Realistically, due to aircraft maneuvering, ascending and descending, the range of research operations will be limited to approximately 500 to 600 kilometers. Next slide. So far, our main source of information about the types and spatial dimensions of polar night clouds is related to 8 trained satellites, primarily CloudSat and Calypso. So just it's worth stressing that so far there were no just any research flight operations during polar night. And this diagram shows a Calypso cross-section. It's one of the early cross-section of just of the cloud fields during the polar night. It's just dated by December. There are 2 distinct types of clouds which you can see on this cross-section. The first type is associated on the left side with the horizontal, thin, strongly attenuated cloud layers. These are mixed phase clouds. And the second type is presented by ice clouds with a variety of different spatial shapes with a vertical extension up to 10 kilometers or higher, and the horizontal dimensions up to 2, 3, or even 4,000 kilometers. For example, on this slide, you can see those clouds on the right. They extended over 1,000 kilometers horizontally. Despite their vertical thickness, these clouds are usually optically thin, and basically these are Arctic cirrus clouds, which in some cases may precipitate down to the ground level. These clouds also referred to as thin ice clouds, TICs, or optically thin ice clouds, OTICs. And I like better the last one because it more accurately describes the nature of these clouds. Next slide. This diagram presents the flight patterns for the characterization of mixed phase clouds. The microphysical sampling will be performed during multiple purposing, horizontal traverses in the middle of the cloud layer, below the cloud top. Aerosol measurements will be performed above the cloud top, below the cloud base, and inside the cloud layer using different inlets. Remote sensing will be performed all the time, specifically the horizontal leg above the cloud top and below the cloud base are important for the FEAR measurements. Typically, the duration of mixed phase cloud sampling ranges from 1 hour to 1.5 hours. Next slide. Sampling of the ice clouds will be conducted at several levels with horizontal legs from 50 to 200 kilometers, depending on the extension of those horizontal extension of those clouds. This includes microphysical, aerosol, remote sensing, and thermodynamics measurements. Duration of ice cloud sampling ranges from 1.5 to 2 hours. Next slide. This diagram presents the flight patterns for ALI measurements. The main requirements for that type of operation is that conveyor tail always points towards the sun, so that the sun remains in the field of view of the ALI optics. The strategy of ALI sampling consists of going to the region of interest and measurements of the aerosol or cloud microphysical profiles, and then flying away further than approximately 280 kilometers so that the sample area remains between the conveyor 580 and the sun, the direction to the sun. The duration of ALI sampling is close to 4 hours, and therefore it requires a dedicated flight. And next slide. Another suborbital component of PONEX is related to calibration validation of EarthCARE. This map shows the EarthCARE descending orbits during PONEX IOP, and the high spatial density of the EarthCARE overpasses creates numerous opportunities for the conveyor underflights. We are considering only descending EarthCARE orbits since their time is consistent with the regular working hours. The timing of ascending EarthCARE orbits is not ideal for the PONEX team operations due to prolonged recovery period next day. So I will stop at that point, and if you have any questions, I will be happy to address them. Thanks.
Thank you very much, Alexei. I have a question about the Kaley profile that you showed. So I was wondering how we can know if those clouds are mixed phase or liquid.
Yeah, mixed phase. Yeah, thanks for the question. Mixed phase clouds, they have a very kind of specific features, and that was described in literature many times. So they are usually for those which are related to Arctic environment. They are horizontally extended. They have a high attenuation. So, for example, LiDAR won't go through. And so they usually have precipitating ice underneath. And so there are just a number of features which are indicative of that they are mixed phase, and they can be identified in flight and also from EarthCARE overpasses before, just during the planning of the flight operations.
Hi, Alexei. That was a nice talk. What frequency are the flights happening? How often? And for example, for the alley dedicated flights, how many flights were you planning?
So far, we were planning, that's based on Adam Barassa and Paul comments. They need a minimum 2 alley flights, but it may be more than that. So we have, in total, we have only 10 flights, so we have to carefully manage our time and dedication to different science objectives and HAWC and EarthCARE missions. But so far it's 2 flights, 2 full flights, because it's a very time-consuming measurements.
Great. Thanks so much, Alexei. And that was excellent. And now we're going to move to the next talk, which will be given by Natalia. So thanks very much.
Thank you. Hopefully people can hear me online. Okay. Good morning, everyone. My name is Natalia Bliankinshtein. I'm a research officer with the National Research Council Canada, working with the Conveyor aircraft. It's as Zen presented in his slides for the first presentation. It's a big team usually working on any airborne research project. Here on the title slides, this is just the NRC researchers who are involved in the work, but there's a big team behind us. Can I use this to switch slides? Excellent. Okay, so for those who are not familiar with us, first I would like to introduce which branch of NRC we represent, and that is involved in the PONEX campaign. So NRC is the biggest R&D organization, federal R&D organization in Canada, consisting of 9 different divisions and 13 research centers. We are a part of the Transportation and Manufacturing Division, Aerospace Research Center. The research center has 4 other laboratories in addition to our flight research laboratory. We are located in Ottawa, very close to the Ottawa International Airport, because we own and operate a fleet of research aircraft, both fixed wing and rotary wing, that are shown here on the slide. So the one implicated in the PONEX campaign is Convenor, which is our biggest aircraft, displayed in the middle of the picture. And the personnel that makes these kind of projects happen is, on the research side, it's the team of airborne facilities for atmospheric research and reconnaissance, but we have a lot of support staff assisting us with that, including engineers from Airworthiness and Instrumentation Department, pilots and flight ops specialists, aircraft maintenance engineers, as well as design and fabrication service department. So as Alexei introduced, the aircraft NRC Convair 580 is it's an old bird. It was built in 1957 and was very productive throughout decades, running different airborne projects. It's basically a big flying laboratory equipped with a lot of state-of-the-art equipment for all sorts of atmospheric measurements. So in terms of the group of measurements that we cover, it includes gas measurements, aerosol, cloud microphysics, aircraft and atmospheric state parameters, as well as the airborne remote sensing. And the picture on the right here is from the Arctic deployment in Kaley that I will talk a little bit about more later in my presentation. So the NRC personnel that enable these kind of projects, we are very fortunate to have a highly skilled, competent, and professional team running the facility and assisting with the research projects. For PONEX in particular in deployment, it's going to be a big crew in Inuvik conducting the research flights, including pilots, aircraft maintenance engineers, avionics engineer, instrumentation techs, and researchers as a cabin crew. But we are also taking advantage of the support that we have at home at the Flight Research Lab, including mechanical designers, fabrication staff, airworthiness engineers, admin assistants, and students involved in the work. So total of 25-something people involved in different stages of any big airborne project. So for this presentation, I would like to focus on a few recent projects that we had, mostly with ESA funding, aimed for the advancement of atmospheric satellite missions, just to demonstrate why we are a facility that is well posed to take on PONEX and why we are primed for success for this deployment. So one of the first projects that we worked on with ESA was spearheaded by Mengistu starting in 2016 for a Doppler wind radar demonstrator for future satellite missions. The objective of the project was to implement on board the aircraft for the NRC airborne WNX band radar a polarization diversity pulse pair mode. That was the first implementation on the moving platform as a candidate for future candidate technology for future space missions, which was successfully achieved in collaboration with cross-sensing from the US as well as universities of Reading and Leicester. And Mengistu and the team were able to measure for the first time high Doppler velocity over 100 meters per second using the PDPP technique from a moving platform. They also collected first measurements of radar cross-section of oceans and land surfaces at incidence angle of over 25 degrees. So this successful work with the NOx radar was a precursor for participation of NRC in the Wyvern mission. So Wyvern Wind Velocity Radar Nephoscope is a candidate satellite mission for ESA Earth Explorer 11, which is currently, the selection for that mission is down to 2 missions. And the concept of this mission is quite simple and quite genius at the same time. It's basically a W-band radar that's conically scanning at a 42 degrees angle, which would allow the Doppler velocity measurements of cloud particle, thus enabling wind measurements in cloud for the first time for the integration into numerical weather prediction models and research datasets. So we had the honor to support the phase 0 and phase A studies for that, led by Con, initiated by Mengistu and led by Con. Phase 0 studies starting in 2022, 2023 were focused on investigating benefits of the pulse compression to improve the vertical sampling of Wyvern, as well as the use of polarimetric radar signals at a slant angle for ice water content retrievals, and as well as studies of radar cross-section of snow-covered vegetation and urban surfaces. After the mission candidates were down selected from 4 candidates to 2, we've continued with phase A to demonstrate the Wyvern radar radiometry capability by measuring nearly coincident 94.05 gigahertz radar reflectivity slant profiles at 42 incidence angle, focusing on the liquid water path retrieval. We've demonstrated it with stratocumulus clouds and warm rain over water, as well as conducted some complementary data collection for ocean currents, currently studied by the French Institute Ephemer. That actually helped with the SWOT mission Calval, because we were able to collect those data in the underpass for that, led by Kuhn. So that's one of the big missions that we are contributing as a research organization and as a airborne facility participating in the pre-launch activities. Some other notable projects funded by ESA include the radar snow experiment. That was a deployment to evaluate in 2018 in collaboration with ECCC and Universities of Region Leicester and Wyoming. The study was focused on Arctic clouds using triple frequency radar and in-situ observations. So the triple frequency radar was the NOx radar with a W and X band, as well as Ka band radar, all mounted on the Convenor, which resulted in the first airborne triple frequency radar dataset combined with almost perfectly collocated and coincident airborne microphysical measurements from a single platform. And this study confirmed results of some previous modeling work with radar dual frequency ratios moving within the different zones of the DFR plane. And for more information, you can check this article by Kuhn and the team. Another project that was more of a technology development rather than naming a particular satellite mission was HISRAMS, led by yours truly over the last few years. The objective for that was to build and demonstrate and flight test hyperspectral microwave technology for the potential application for all sky retrievals of temperature and humidity. So as you might know, the microwave sounders in general are one of the most common sources of information used for NWP models from the existing satellites, as well as hyperspectral infrared technology is widely used. And this was the first attempt to combine the benefits of the hyperspectral resolution with the microwave abilities of see-through clouds. We were able to design and build with our colleagues the novel HISRAMS sensors. It was the big team effort with Swedish company Omnisys Instruments, since then acquired by AAC Clydespace, McGill University, and with some complementary funding from the Canadian Space Agency. We collected the first airborne microwave spectra. We were able to validate them, and as well as the retrievals in clear sky conditions, and compare them against the hyperspectral infrared ground-based ARI sensor, and as well validated the spectra in presence of warm clouds using synergy with W-band radar radiometer. On that, the article right now is in preparation by Leilio from McGill University. So this instrument, since its conception and since the successful conclusion of the first project with ESA, has been remaining at NRC on the long-term loan from ESA, and it's going to be part of the payload for the PONEX campaign in the Arctic. And that leads me to two recent campaigns that were conducted in the last year. One is wafers, and Raphael will talk more about it in the following presentation. Wafers was a multi-platform, multi-frequency field campaign conducted over Ottawa and Montreal in January, February of this year. Wafers stands for W-band, HISRAMS, ARI, FIR2, FINESS, and FIRMOS, Experiment on Remote Sensing. I got shout out from our pilot for making an acronym out of acronyms for that one. So all these different names are different sensors, some of them microwave and some of them infrared and far infrared. And the purpose of that was to achieve the radiative closure in all of these bands for the multi-platform measurements, observe snow and ice surface emissivity, and explore synergy of active and passive sensors for atmospheric retrievals. So some of the sensors were on the Convenor, some were based on the ground at Cold Reserve near Montreal and in Ottawa, complemented with radio zone launches, and as well as satellite overpasses of pre-fire. So the resulting data set that we are massaging right now will advance the development of microwave far infrared space missions, including assistance for the HAWC tick fire, ESA forum mission, and the US pre-fire. That was a big team effort with international collaborators as well. So ESA, NASA, Imperial College London, National Research Council of Italy, ECCC, McGill, UQAM, and National Research Council. And the last one I will mention very briefly, because Japan will have a dedicated presentation in the afternoon session, is the calibration validation campaign for EarthCARE Echolot, where we were based out of our home base in Ottawa, and we were able to conduct 7 successful underpass flights in various seasons and various meteorological conditions for validation of this satellite. On the NRC side of things, this effort was led by Kuhn with the research contributions from Paloma Bork and Kevin Rajbar. So that concludes the overview of the recent projects. And to wrap up my presentation, I will show some of our engineering work in preparation for PONEX. So as Zen mentioned, the airborne FEAR has been installed already for the wafers flight campaign and flight tested in anticipation for PONEX. So to make that happen, so the spot that we selected for the installation is the nadir belly pod that is under the aircraft floorboards, and the instrument had to be repackaged by the manufacturer to fit in that tight space. Also, FEAR 2 normally, as a far-infrared instrument, requires an unobstructed view of the atmosphere, but our aircraft is pressurized and we would like to keep it so. Therefore, we had to select the appropriate material as a window for that, which ended up being synthetic diamond. The windows were procured and tested to maintain pressurization and installed on the aircraft. We were lucky to leverage some ESA funding for this modification through the wafers campaign in anticipation of PONEX. So our mechanical designers pretty much took care of making sure that the installation accommodates the instrument as well as the aircraft structure, and got approved for flight by our airworthiness department. And airborne alley right now is in the process of being prepared for integration. So the instrument that we're using for that is the University of Saskatchewan instrument prototype that was flown on the stratospheric balloon in Timmins, and we are installing it in the cabin next to a window so that it would look aft limb using a periscope. And here are some schematics of that installation. And the periscope will be adjustable to tune the field of view, and sealed and purged with dry nitrogen to remove any condensate on the optical parts inside it. So just a repeat of some of the milestones that Zen already shown is basically right now, as Alexei presented, we are actively compiling the flight plans for different research objectives and trying to decide the time allocation for different priorities. It will be followed by the instrument integration and the worseness processes, preparation of deployment logistics, packing up, going to Inuvik, collecting data, then diving into data analysis before eventually the data sets for this campaign will go public. That's all I have. Thank you.
Thanks very much, Natalia. Any questions? Or online?
Nothing online yet.
Any questions in the room? Yes. 1 second.
Thank you, Zen. Thank you, Natalia, for a nice talk. For the FEAR too, it's really not desirable to have the diamond window not included in the calibration pass. So what are you thinking of this? Is possible maybe in future this aircraft can be reconfigured to allow this part to be included? And maybe related questions maybe for Maple, for the design of future facilities, how can we make the aircraft capable of accommodating this kind of radiometric measurements from air?
Thank you for the question. Yeah, so these are all considerations that went into the design of the integration when we were brainstorming it about a year and a half ago. I think we were looking at option of having the front end of the instrument outside of the pressure envelope to mitigate that, but that kind of installation was engineeringly a lot more complex and prohibitively expensive because of that. So some options to not have to deal with the windows in the field of view of FEAR would be to fly and unpressurize the aircraft, but in that case, the altitude would only be limited to 10,000 feet, or a significant engineering upgrade to make sure that the whole front end, including the receiver and the black bodies of the instrument, is outside of the pressurized zone.
So it's possible, it just takes more money. That's
pretty much.
Thanks.
Thanks, E. Any other questions?
Thank you.
Thanks, Natalia. And our next presenter will be Raphael. Perfect. Who's going to talk about the fear measurements during wafers.
Okay, thanks. Good morning, everyone. My name is Raphael Peroni. I am a postdoc at the University of Quebec at UQAM. Today, I'm going to show you a brief overview of the wafers campaign done at the beginning of this year, and I will show you some example of measurements done by the different instruments on board the conveyor and by the FEAR 2. So firstly, I will talk about the campaign itself. Then I will show you example of measurements done during wafers and data observed by the FEAR 2 for 2 flights, one in clear sky condition and another one in cloudy sky condition. And finally, I will briefly talk about the FEAR 2 preparation for PONEX. So the W-band ESRAMS IRE FEAR 2 finesse and CMOS experiment on remote sensing, wafers, is an international collaboration done at the beginning of this year from January 7 to February 14. The objective of wafers are to perform radiative closure experiments and investigate the consistency between the simulated and measured atmospheric states at the surface, within the atmosphere and to the top of atmosphere. To cloud signatures measured by the microwave, thermal, and far-infrared radiometer, measured radiance compared to atmospheric states measured by in situ and active sensors, to assess the feasibility to retrieve cloud properties with microwave and infrared synergy, evaluate and validate theoretical models of snow and ice surface emissivity, to have a reference dataset for airborne and satellite measurements, and investigate the temperature dependence and implications for TOA remote sensing. The wafers brings together instruments covering far infrared, thermal infrared with airborne sensors, combined with ground-based instruments operated at the CNRC Flight Research Laboratory and at the GOAT sites at Mont-Saint-Hilaire in Quebec. And as you can see on this slide, a lot of instruments were deployed during the campaign. But for now, I will focus on the far infrared radiometer model 2, the FEAR 2. It is an innovative passive atmospheric radiometer, initially operated from the ground, but recently redesigned for nadir viewing on board the Convair 580. FEAR 2 is a prototype and a technological precursor for the TICFIRE instrument. And the detector is based on the microbolometers technology, and the instruments provide radiometrically calibrated radiance and brightness temperature in 8 spectral bands, from 7.9 micrometers to 27.5 micrometers. The far infrared region from 15 to more, it's a great interest for water vapor and ground microphysics properties in very cold and dry environments. And on the right, you can see the normalized transmittance are the function of wavelengths for the 8 spectral bands. And on the left, you can see a picture of the FEAR 2 installed on board the aircraft, the Convair 580, next to its computer. On this slide, I just wanted to show you the aircraft trajectory, the 2 maps on the left for the 2 selected flights. For one clear sky flight done in January 22. This flight was very interesting because it was done during the descent of a polar vortex to the south of Quebec. So it's really good reference cases for PONEX. And the second flight, the February 2, was done mostly in ice, with thin ice clouds. and a few clear skies and liquid mixed phase clouds above Ottawa. On the right, you can see the aircraft trajectory as a function of times for the 2 selected flights. Here you can see example of measurements done by the airborne elastic cloud LiDAR pointing at Denit operated by Kevlar in the Convair 580. This figure showed the depolarization ratio measured from the top of the aircraft to around 10-11 kilometers. And on the left, I show you a plot of the attenuated backscatter signal measured by the Halo Doppler LiDAR operated by Amélie Sauvageau at the GOAT site in Mont-Saint-Hilaire. And what we can see on these 2 plots is that the flight was done mostly in clear sky condition. We cannot see a lot of clouds. And here is what we got with the FEAR 2. So on the left, you can see the bottom panel, the radiance measured by the FEAR 2 are the function of time in UTC for the 8 spectral bands, so 1 band, 1 color. And the black curve represents the aircraft trajectory. And the top panel shows the brightness, the derived brightness temperature. And this flight was done mostly in clear sky conditions, so the variation that we can see could be explained by the humidity atmospheric variation or the temperature and surface emission variation. And on the right, you can see the humidity profiles measured by a weather balloons launched by Benjamin, PhD students of EE at the GOAT site. And these profiles are really useful for constraining the radiative transfer code if you want to compare FEAR 2 with models or ground radiometers such as Finesse CMOS or IRI. This slide is the same as I showed you before, but for the second flight, the cloud sky flight. And the difference is that we can see a lot of clouds, mostly composed of a lot of large crystals, bigger than 100 micrometers. And as you can see on these 3 images from the CPI probes on board the Convair operated by Paloma Borg, there is a lot of aggregates, bullet rosettes, and some columns. And this is what we have for the FEAR 2 observations during this flight. Same as before, we have on the bottom panel the radiance measure, and the top panel the brightness temperature derived from the radiance measurements. The different stars show you where the ice crystals, as I showed you before, were sampled during the flight. And during this flight, we were able to fly below the cloud, inside the cloud at different altitudes, and above the cloud. So it was a really nice configuration because it gives us vertical information on the microphysics inside the cloud. And on this slide, I just want to show you what we can do with these measurements. So here, this figure represents the anomaly of radiance and brightness temperature. So the anomaly is defined as a difference of radiance and brightness temperature between the clear sky flight and the average value computed with the clear sky flight measurement. And according to the flight altitude and cloud optical depth, the anomaly could be explained by either a combined effect of the microphysics inside the cloud, the humidity, the atmospheric humidity, the temperature and surface emissivity, or only an effect of the atmospheric humidity and the ice crystal size and shapes. So So to conclude my talk, FEAR2 data have yet to be calibrated, but they are highly valuable for understanding the effect of thin ash clouds on the tear and FEAR spectral domain in cold and dry conditions. And it will be necessary to deepen the analysis and identify more precisely the effect of ice crystals, as well as temperature and surface emissivity and the effect of water vapor. And then to perform radiative closure experiments. But the first campaign was a great opportunity to validate FEAR2 operation and get ready for PONEX, because FEAR2 will be involved during PONEX, and PONEX will be the first FEAR-ALI synergy. So it will be a good opportunity to simulate synergy between TICFire and ALI. Thank you for your attention.
Thanks very much, Raphael. Any questions online or in the room? Yes.
Thank you very much, Raphael. I just wanted to know if TICFire is sensitive to aerosol as well, and if yes, it's sensitive to size or concentration.
I don't think TICFire will be sensitive that much to aerosols. It will be more sensitive to water vapor.
Yeah, because, for example, in satellite data, for band 10 and 11 micron, you can see the signature of dust.
Yeah.
So I guess probably here also we can see something.
Yeah, probably. Yeah. But I think it would be the job of the synergy between ALI and TICFire.
Yeah, I asked this question because ALI is best at altitude higher than 5 kilometers, so I thought that maybe. Thank you.
Thanks. Any other questions?
Nothing online.
Nothing online? Great. Thanks so much, Raphael.
Well, thank you.
It's a great talk. And our next presenter will be Adam Rasa on behalf of Paul, who will be talking about LE. So we just heard about synergy between FEAR and LE. And so that's something Adam's going to talk about. Thanks, Adam.
Okay, yeah, thanks everyone. Thanks, Zen. This has been a really nice and interesting session so far. So I'm going to tell you a little bit more about ALI, the aerosol limb imager. And I'll just review exactly what that instrument does as part of the planned HAWC satellite mission very quickly. I'll tell you about the development stream of ALI, how we've built some prototypes of the instrument at the university, and how we've tested that prototype on stratospheric balloons and successively advanced it to the state it's at today. And then more recently, the Canadian Space Agency funded the build of another prototype that was specifically built to fly on the NASA ER2 high altitude airplane. And I'll show you some results from that campaign. And then I'll finish by just talking a little bit about the planning and the expectations for ALI as part of PONEX. You've seen this slide before a couple of times at CMOS, but ALI is part of the HAWC satellite mission, which is planned for launch as part of the much bigger NASA AOS mission in around 2030. It is one of the two limb sounding or limb imaging instruments that look at the side view of the atmosphere and measure the vertical profile that is aligned with the nadir measurements that are on the NASA satellite, as well as TICFire. Okay, and so ALI is specifically developed to measure aerosol profiles. The retrieval products are aerosol extinction, aerosol effective radius, and a detection of thin cloud top layers like subvisual cirrus. From something like 5 kilometers, although PONEX is really going to stretch us here to see how low we can really go, up through the stratosphere to the top of the stratospheric aerosol layer. And the concept, at least the current concept of the instrument, Honeywell is working on this, looks like this, where ALI will take basically two-dimensional pictures of the side view of the atmosphere. Each one of these pictures is at a specific wavelength, narrowband wavelength range, and at a distinct polarization state. And as the instrument flies along, it's able to rapidly take these images and change the wavelength between the red end and the shortwave infrared at about 10 different channels. And it's able to change the polarization of the images. And together, this long spectral range and the dual polarization lets us discriminate between spherical aerosol particles and ice crystals, as well as retrieve some information about the particle size distribution. Okay, so we started to conceive of this concept a long time ago now, more than 10 years ago. And through a series of CFI and Canadian Space Agency FAST grants, we're to develop successively advanced prototypes of this instrument just within our university lab. And we've flown them on several CNES stabilized stratospheric balloon flights, starting in Timmins, but we also have been to Alice Springs, Australia, and to Kiruna, Sweden. And the instrument really is pretty compact. It's about the size of like a couple of toasters kind of thing. It would sit on your countertop quite nicely. It basically consists of an input telescope, the spectral and polarization selection mechanism, and some imaging optics in the back end. And so you can see it here just sitting in the corner of one of these CNES stabilized balloons on its way up into the stratosphere. And from the float altitude of the balloon, which is way up above the ozone layer at something like 35 to 38 kilometers, this is a sample of what the spectral imagery looks like. So here, this is an image taken in the horizontal polarization state at around 1 micron, 1025 nanometers. And here's the same image taken like 1 second later in the opposite polarization. And here you can see the cloud deck below around 9 kilometers. And then where the image looks actually very boring is really where the stratospheric aerosol information is, here above the cloud. And it's the polarization information together with the spectral information that tells you about the aerosol that's above the cloud. And I think with your eye, you can see a little bit of the difference between these two images just in the color scale there in the aerosol layer above the cloud. So if you were to take some sort of vertical cross sections out of those images and look at just the profiles, you can use the dual polarization to derive a degree of polarization. And where that degree of polarization has a distinct change, that's telling you you're moving from a regime that's dominated by spherical aerosol scattering to ice crystal scattering. So that's a nice way of detecting the difference between aerosol layers and cloud layers. Yeah. And then you can also, above the cloud, try to retrieve some things like aerosol concentration and aerosol particle size parameters. Here we're retrieving median radius and some sort of a constant distribution width in altitude. So this is actually a nice case. This is from a 2023 flight in Timmins. And you can see that there's quite an enhancement in the aerosol radius, right around 22 kilometers. And this is the remnants of the Hunga Tonga volcanic eruption that eventually made it all the way into the northern hemisphere and persisted for quite a long time. Okay, and then I mentioned that the Canadian Space Agency has also built their own prototype as we prepare for the satellite flight of this instrument. This is purpose-built for the NASA ER2 airplane. It was built by Honeywell Aerospace. And it was flown in 2023 together with the prototype of the SHOW water vapor instrument. This was quite a neat flight. I don't think this has really ever been done before on the NASA ER2, where we had 2 limb imaging instruments. They were both accommodated in one wing pod, where here, if you look at the wing pod here of the ER2 flying at altitude, there's a hole in the front of the wing pod. That's where the water vapor instrument was able to look out at the side view of the atmosphere. And then way back here, you can see this little black box that's hanging down below the wing pod. That's the periscope that Ali used to look out and image the side view of the atmosphere. So these 2 instruments were together viewing the limb. And here you can see the Ali electronics and optics box sitting inside the wing pod of the ER2. So we did 3 flights on the ER2, just based out of NASA's Armstrong base in Southern California. The first one was a short engineering flight, shown in blue here, where they just got up to altitude and basically spun the jet around at a bunch of different angles just so we could test the dependence of the signal with respect to the sun. And then we did 2 longer science flights with these north-south legs timed with satellite overpasses of water vapor and aerosol measuring satellite instruments. And here's a sample of what the spectral imagery looks like from the ER2. It looks qualitatively quite similar to what we saw from the stratospheric balloon, where you can pick out the cloud top really quite easily, and then there's aerosol information here above the cloud top in the spectral and polarization dependence. So as you look through these images, the wavelength is changing, and what's labeled here as the LCR, that's the liquid crystal rotator, that's the component that changes the input polarization state between horizontal and vertical. So the LCR is flipping between on and off states here, and then you take all of this imagery together in a single retrieval and find the cloud top, retrieve the aerosol concentration, and retrieve the aerosol radius. Now, what we found actually is this sort of key component that does the spectral selection, the acousto-optic tunable filter, actually did not perform very well at all. It's hard to see by eye, but there's some spectral ghosting here. For example, you can see the left side of the image looks brighter than the right side of the image. That's an instrument artifact that was very hard to deal with and basically sort of really hurt our ability to do scientific retrievals. And this was part of the Canadian Space Agency's decision to look for an alternate spectral selection technology for LE. There's lots of ways that you can collect this data set, so it's not too much of a worry. We'll probably just end up using a filter wheel or a grating. But it's a bit sad for me because this is a cool technology and we worked on this for like a decade in our lab. So to not see it make it to space is a bit sad. However, we were still able to do some interesting aerosol retrievals from the ER2. So what we're showing here is latitude along the flight path of the airplane and then altitude. And this is satellite data from the NASA OMPS satellite showing aerosol extinction and cloud extinction. So basically here's a cloud and here's an aerosol layer sitting above the cloud. But when we fly with LE, we can obtain much, much better vertical and horizontal information. So you can see the edge of the cloud here is all this sort of interesting, complicated structure. And you can see actually multiple sheared aerosol layers above the cloud, which are sort of much beyond the current state of the art for what OMPS is able to do. And these are sheared aerosol layers that are also remnant plumes from the Hunga Tonga eruption. Okay, so just a couple last words then about planning as part of PONEX. You've seen some of this before already, but a similar approach will be used for LE as we used on the ER2, where we'll use a periscope, which Natalia showed you here, which is going to be designed and fabricated by NRC to allow LE to be inside the aircraft and then to look out and backwards to image the side view of the atmosphere behind the airplane. And Alexei showed you a sample of potential flight planning where we would ascend to altitude, basically use the Convair in high altitude straight level flight to simulate the sort of satellite geometry that LE needs. At the end of one of these flight legs, we would do an in situ profile, make a FEAR measurement, and then fly back along the same path. And with LE flying back along the same path, it's able to look out at that spot and observe the cloud and aerosol profile that was just measured in situ and by the FEAR. Okay, and so we've done a few simulations of how we expect LE to perform as part of PONEX. So the first thing we tested was to just use a radiative transfer model to simulate the scattering from background aerosol with a cloud layer at 3 kilometers. And then to simulate the aerosol measurements and derive this degree of polarization. And you can see that the polarization does indeed switch quite sort of rapidly from one state to another when you hit that cloud top. And then you just use edge detection and P to identify that cirrus cloud top layer. So we think that the cloud top layer detection will be really quite robust and work quite well. I do have some hot off the press aerosol extinction retrieval results just from the one group member of ours from this morning, but they couldn't make it into my talk today. But it does look like the extinction particle size retrieval works reasonably well in clear sky conditions or above cloud top. But we do have to make some assumptions about what the aerosol is above the PONEX altitude. And that could be a little bit of a problem. So we'll have to rely on satellite overpasses probably to tell us what's happening above the satellite or above the airplane, sorry. Okay, so then just some conclusions. LE is being developed for the HAWC satellite mission to measure sulfate, smoke, and dust from the mid-troposphere through the stratosphere. We've got these prototypes that we've flown on stratospheric balloons and on the NASA ER2. And we're excited to try and take part in PONEX. Thanks to NRC for the support on designing the periscope and helping with the integration. Thanks to ECCC for the campaign planning and logistics support. And we're looking forward to learning about LE capabilities in the Arctic and at low altitudes. Okay, thank you.
Thanks, Adam. Any questions in the room or online? Natalia.
Thank you, Dan. Thank you, Adam. I actually have two questions.
Sure.
One question is the technology for the spectral selection that you mentioned that's not going to make it on the satellite. Is it the one that's used in the box that we're installing?
It is, yeah.
Are there any implications to the data because of that?
So in the prototypes we built at the university, we used a small acousto-optic filter, like a 10 millimeter one, and it seems quite robust and it works fine. For the satellite, we need a larger aperture device. And when we scaled the crystal size up to larger aperture, that's when we started to observe the problems. So I think we're quite good actually for PONEX using the University of Saskatchewan prototype. Yeah.
Good to know. That's great. And another question. So about the aerosol profile above the flight altitude, could you be able to measure it with Ali if you were to look up a little bit from the aircraft?
Yeah, we're actually trying to learn about that with the simulation. With the limb viewing geometry, the sensitivity really comes at the tangent point. So basically where the line of sight is closest to the Earth's surface. And when you look up, then you lose the tangent point. The tangent point's actually behind you in the geometry. So there's very little actual vertical information when you look up, but there's maybe some. So that's something we need to try with the simulation.
Hi, and thanks for your interesting talk. Just a quick question for the same question you just asked about above the flight. Could you launch like a balloon to the stratosphere with something on it to get you that information?
Yeah, that'd be really nice. Unfortunately, to measure stratospheric aerosol, you need quite a complicated balloon payload, not something like a typical weather balloon could support. So if we could have a real stratospheric balloon launch as part of PONEX, that would help.
Yeah, that was a dream, but we kind of had to leave that dream by the sidelines, at least for this campaign. Would you get enough out of ATLID, for example?
Yeah, I hope so. I think a combination of probably OMS LP and ATLID would be quite helpful.
Yeah, so at least we've got what we think are close enough to sufficient measurements to at least establish that. And then when we think towards our next suborbital campaigns, what do we actually really need to accomplish this?
I think so. And I mean, the uncertainty with the aerosol above is going to create some sort of static bias in what LE retrieves for extinction. So we'll still retrieve the layered structure. We just might have a bias somehow. Yeah.
Thanks. Yes.
That's where the mystery factor comes.
I just want to very quickly comment, it's not just aerosols at high altitude, and possibly even clouds, clouds.
Yeah.
If we want to deploy also ground-based radiometric measurements, I think the information at those high altitudes are quite critical.
I agree.
Thank you.
Yeah.
Thanks, E. Yes, Leonid.
Have you previously done any comparisons of in situ with Ali in previous flights?
Yeah, we've tried to do that with the stratospheric balloon flights. We did have one flight where we had optical particle counters on the same payload. It turns out that's actually quite hard to do because the remote sensing observation is sensitive a few hundred kilometers away from the balloon. And also on that balloon flight, Kness was dumping ballast off the balloon, and every time they dumped ballast, the particle counter would observe some dust or something that was coming off the ballast. So that basically we tried, but the measurements were contaminated. Yeah.
And in situ extinction.
Yeah, exactly. In situ extinction, we've never had that available before. Yeah.
That slide you showed with the results from the ER2 campaign,
Yeah.
where you could see the artifact, the imaging artifact from the
Yep.
AOTF. How did you resolve that? And can it be used in the PONEX campaign to resolve if you see that?
Well, so remember this artifact comes from the 20 millimeter AOTF, which is not used in the ALI instrument, which will be on PONEX. This was bad enough that the channels that showed this behavior had to be neglected from the analysis. Yeah.
So you lost a quarter.
Yeah.
Thanks. Any other questions here or online?
Nothing online.
If not, thank you very much, Adam.
Good. Thanks, Zen.
And we've got one last talk before lunch, which is, Julie. So Julie's going to present one of the surface sites that will complement PONEX.
Thank you. Can I use this? Yeah. Okay, super. So good morning, everyone. I'm very happy to be here today to talk about these initial results we have. So it looks like it may not be related to PONEX, but I heard about PONEX at the Maple workshop, and then I connected with Zen and realized that TVC was really close to Inuvik, where PONEX was. So then today, this is, and our project was going on during that time. It's now finished, and we hope we could eventually continue. So I'd like to acknowledge, before I continue, so I'll talk about precipitation measurements in the Arctic, in particular at the Trail Valley Creek Research Station. And I'd like to acknowledge my co-authors, so Hadley Thompson and Joseph Duras, who installed the instruments in the Arctic and also took the manual observations during March. And also my co-author and colleague, Phil Marsh, who led this grant of frontier exploration that we got to do this work. So Trail Valley Creek Research Station is located around 50 kilometers north of Inuvik. So this is where the PONEX experiment will be held. And then Trail Valley Creek is just north of it. And it's managed and maintained by Wilfrid Laurier University in Ontario, by Phil Marsh, actually. And one of the main remaining questions at this site, and what Phil has been trying to do for years, is how much snow falls at TVC. We still don't know. And this is research station, like as I said, is located in the Canadian Arctic. So there's a few challenges associated with measuring snow that falls, not necessarily snow at the ground, but snowfall. And one of the main challenges is wind speed. So when it snows, let's try. Okay, so let's look at here. So when it snows, here we see precipitation accumulation. We have wind speed on the side. So we have different gauges installed on the same site. And then we see that when the wind reaches here around 10 meters per second, none of the gauge gives the same answer. So most of the gauges used are those placed in a single alter shield, where here it measures the lowest amount. Environment Canada is getting up to the double alter shield, I think. And then there's a little bit more precipitation. And this is the reference gauge, the DFIR, now called the DFAR. So I've put pictures of them here. So we see a lot of differences between the gauge. And then we organize it as the collection efficiency. So let's say the collection efficiency of single alter over the DFIR. And then we organize through wind speed. Then we see that the collection efficiency decreases with wind speed, but also what we see is a lot of scatter in the data. So existing transfer function that we can use the universal transfer function, for example, from SPICE, available in Kochendorfer 2017, use basically the wind speed and also the temperature to try to sort the phase of the precipitation. But then this is work that we've done some time ago now, that we show that the microphysics plays a role. So the SPICE transfer function with the wind speed will give you one value for one wind speed, but then we showed here that the microphysics can play a role. So if we look at the box plot here, we have, this is the data that was collected at the site at NCAR in Boulder. And the solid lines are simulations. So we did the CFD simulation trajectory calculations, and we've seen that for dry snow that fall faster, it falls less in the gauge because their trajectory is deviated away from the gauge. But those that fall faster, like wet and rime snow, will fall more in the gauge. So the microphysics explain a lot of the scatter in the data. So in 2020, Matteo developed a transfer function that used the snowfall rates. So using the snowfall rates and the wind speed allowed to take into account the particle size and eventually the fall speed. So additional challenges: measuring solid precipitation in the Arctic, strong winds leading to blowing snow. Automatic gauges have a lot of difficulty to differentiate falling precipitation and blowing snow. And also the measurement of light precipitation. So in terms of amount, the light precipitation in the Arctic can be up to 50% of the annual total amount of precipitation. So in this project, well, we're trying to know how much snow fell in 2023, 2024. So we tried to develop a method to estimate the annual snowfall amount at the TVC research station. So to do it, we use a combination of manual observations and automatic measurements. So now we use only the gauge located in the single alter sheet and the microrain radar that was at the site. We also had a Parseval distrometer and a hot plate, but we had a bit of difficulty having them run and not having a noisy signal. So at the end, these are the two instruments we use, but I think that the Parseval would give us more information and help us to solve this issue of snowfall measurements. So how the data was analyzed and collected. So we had instruments, automatic instruments installed on November 4th. Well, it started running on November 4th. We aimed to start at the beginning of the season, but 2023 was a big wildfire season, and Yellowknife was shut down when we were supposed to go. So our planning was a little bit perturbé. So then we don't have the full year of measurements. And then we took manual observations. So manual observations are just trying to take photos or trying to see if it's snowing or not at the site. So we used the GeoNord data. We adjusted using the Kaley transfer function. And then we use the MR data to try to fill in the gap into those light precipitation events. So this is a picture of some of the instruments that are available and are measuring at TVC. Okay, so Joseph was there for about 2 or 3 weeks, taking manual measurements whenever something was happening, either blowing snow, light precipitation, snow. And so this is differentiated by the colors here on the graph. This is the accumulation, this is the time. And then we noticed, I was hoping to see some signal for blowing snow, but we didn't see anything. So when there's blowing snow in purple, there's no differences in the gauge measurements. Well, here we see a big jump. This is capping. The temperature increased to close to 0. There was a dump in the GeoNord, so we see that. We see here light precipitation. Well, we think this is light precipitation, but they had to go back to Inuvik to get food and gas, so there was no observation, unfortunately, that day. But we think this is it because other instances show that when the GeoNord is not measuring and the MRR is measuring, it was light precipitation. And there's also snow here. So the way we define light precipitation is that Joseph was outside trying to collect snow on a collection pad. He was able to see that there was snow or ice crystals, but he was not able to do anything, any photos with it. So at this time, then he was writing it down, and then we could look at the behavior of the data, comparing the data with, between the gauges. And this is an idea of the sample number of hours that were collected. So we see that the snow observed, GeoNord detected it maybe more than half of the time, the MR all the time, and the light precipitation 2/3 of the time maybe was detected by the MR. So we use the MRR then to try to estimate the snowfall for the whole season. And then after we use only when the precipitation rate is less than 0.2 millimeters per hour, because that was the lower limit of the GNR. So the GNR just started to measure, or we can only trust the data at that value. So we tried with the existing literature. It was giving some extreme values. So we tried to get like our own coefficient for ZS. And then the amount of the MRR accumulated precipitation was not bad compared to the adjusted GNR. There's still, I think, some work to do here. So this is preliminary results, but I think it gives some promising results. And then we can see the high occurrence of low precipitation rates. So if we look over the season, 2023-2024, we see here in red, the unadjusted GNR, the lowest amount, about 60 millimeters only was detected. When we adjusted for the wind speed and precip rate, then it goes up to 172 millimeters. And then when we add the contribution from the light precipitation not detected from the MRR, then we get to 250 millimeters. And so what's the contribution of the light precipitation if we divide it by the number of days for a daily accumulation? So if we look at the unadjusted GNR, when there's 1 millimeter, well, we can see here the number of days is much higher for the 1 millimeter daily accumulation. So 50 days for the unadjusted GNR. And then this go down when you adjust it because you cannot add precipitation to 0. So then the unadjusted GNR is multiplied by an amount. So the adjusted GNR just moved to higher amounts. And then we can see that then the MRR is able to add this additional number of days to 65 days in this case. So for each daily accumulation, so we can see that in blue it's the MRR and the purple is the adjusted GNR. So we can see that more than 50% of the seasonal 1 millimeter daily accumulation is from light precipitation, according to this calculation. And when the daily accumulation is less than 5 millimeters, it's 33 millimeters over 215. So that's not negligible. However, if we look at the longer days, then we see that the contribution for light precipitation is not as important. And it is just probably because there's not that many instances of those events. So to conclude, I think, estimated not bad the seasonal snowfall for 2023-24. The manual observations in this case were key because we were able to identify and define, in this case, our definition of light precipitation because it varies in the literature, that definition. So the light precipitation and which instruments was able to detect it and making sure it wasn't blowing snow, for example. And then the contribution from the radar is about 24% of the adjusted GNR. So when I say we are able to estimate it, what I'm not 100% sure because what is the truth? So our colleague hydrologists are doing now comparison with the snow surveys and then trying to see if the amount of precipitation that we provide them is able to match their data at the end of the season. And then also we need to compare different transfer functions because this can have a huge range in the number of the adjusted solid precipitation. So thank you.
Thanks very much, Julie. Any questions online or here in the room?
Is there any satellite data products that can differentiate between the precipitation part and the blowing snow part?
Probably. That's a really good question.
Have you looked into?
No, not yet, no. Yeah, very good question.
Thank you very much, Julie. So my question is a bit far from your presentation. I just wanted to know, is it possibility to add a flux tower there, at least for during the campaign?
There is one.
With
At
gas
TBC.
measurement?
It measures water vapor and CO2 probably, but we this afternoon we can talk about this. Phil will be here and we can see exactly what is there and available.
Yeah, that would be great,
Yeah.
because I know Geological Survey Canada, I had a discussion with them. They have flux towers, but just during summer. So they
yeah.
have issue to run it in the winter time. So
Okay,
we
yeah, I
can
think
talk
there's
about
flux
that.
measurements at the site for sure. Then
Okay,
we
that
can
would
look
be
at the
great.
details.
Yeah, thank you.
Mhm.
That concludes the morning session. Thank you, everyone. And now it's time for lunch break.